disperse energy over as many microstates as possible. But practically, it's difficult to measure the number of microstates. So what we need is a thermodynamic parameter, entropy, but related to a parameter that we can measure. And it turns out heat is that parameter that we can measure. And when you think about heat and work, you would probably associate entropy with heat over work. And why is that? Well, work is a concerted action of particles, all moving in the same direction to compress something. There's relatively few microstates involved with all the particles moving in the same direction, where heat is the random motion of particles. And there's many microstates involved in the random motion. So heat is the more naturally associated parameter for entropy. And you can think of that. Here's a ball bouncing. You know when balls bounce, the natural process is for them to slow down, bounce lower and lower each time. And that's because energy is moved from the ball moving in a concerted motion to random motions of a slight raise of the temperature of the surface. Slight raise of temperature, more random motion of the molecules in the floor. And of course, that robs some of the energy and you get a lower bounce. And more energy is distributed into microstates in the floor. That's the natural progression of things. Energy to move into many microstates. Now, if you think about a ball sitting on the floor, we never observe the opposite. That is, the ball just spontaneously bouncing, because that would mean all the particles in the floor move in a concerted motion, suddenly go to a lower entropy state and impact the ball and raise it off the surface. So balls don't spontaneously bounce because that concerted motion is a low entropy situation. Now, how do we measure this heat and entropy? Well, it's very closely correlated. The entropy change is given by the heat evolved in a system over the temperature. So when a system, for instance, goes from bringing a cool and a hot system together, we can measure that by the heat transferred. Heat always goes from a hotter system to a cooler system. In fact, some people call that the second law of thermodynamics. Heat always moves from hot to cool. Now, you can never get two systems that are at the same temperature to have all the heat spontaneously move to one side. That would be like all the particles moving to one side of a container and leaving a vacuum on the other side. That's not the spontaneous direction, not the favored direction of the universe. So, two warm systems, if I go from hot to cool, the heat moving from hot to cool, we can see the entropy change and why that is favored overall. So if we look at our definition of entropy, that is, the change in entropy is the heat evolved over a reversible process at a given temperature, you can say, well, what about a hot system releasing some of its heat, so that's exothermic, I've made it negative, and a cold system absorbing that same amount of heat. So the amount of heat released by the hot system divided by the hot temperature, and that same amount of heat going to the cold system divided by the cool temperature. You can see already this entropy change is smaller than this entropy change. This has a high temperature. So this negative entropy, this decrease in entropy, is small. This increase in entropy, because the temperature is lower, is large. So the heat that moves has a bigger effect on the entropy of the cold system than the hot system. And there's kind of an analogy. Think about it if you were to sneeze in a crowded room, a hot, noisy room. That sneeze wouldn't have much effect. But think about that same sneeze in an absolutely quiet, cool room. Then there'd be a big effect of that sneeze. So you're seeing that same thing. The same amount of heat transferring have a bigger effect on the entropy on the cold side than the hot side. So if you add those two, you find that the overall entropy increases. Now, what if the temperature changes? Well, we can simply add up, divide it into tiny steps, and add up all the individual temperature changes at constant temperatures. So we transfer a little heat at one temperature, then transfer a little more heat at a higher temperature, transfer a little more heat at a higher temperature. The sum of all those becomes an integral. Now, we're not going to do any integral calculations in this course, but you may know if I take the heat, I can represent that as the heat capacity times the change in temperature. And adding all those individual Cp delta T's, I can calculate that the entropy change for a change in temperature is the heat capacity times the natural log of T1 over T2. So the temperature change and the heat capacity determine the entropy change if the temperature changes. In fact, it's very strongly related to the heat capacity of the system. It determines how the entropy changes in the system. So thermodynamic entropy is related to heat. It's related to the reversible heat, but in many cases, delta S is a state function. So we can find the reversible heat, imagine a path that has reversible heat, measure that heat, and use that in our entropy equation. Delta S, Q reversible over T, gives us a way to measure heat and calculate entropy. Much easier than taking microstates and trying to count them. The statistical and thermodynamic versions of entropy, turns out the thermodynamic one much easier to measure.